Hello, in this video I'm going to talk about the Laplacien of Gaussian. But first, let me tell you why we do need the Gaussian function. So basically, if you convolve an image with a Gaussian, what we are doing is filtering out high-frequency components. And since the noise is made out of high-frequency components, removing these would reduce the effect of noise. Therefore, before applying the Laplacien on an image, we prefer to convolve it with the Gaussian function to reduce the effect of noise. So after performing this convolution, what we would do is to calculate the Laplacien of this operation. So the Laplacien is basically the second derivative in x and y, and since the derivative is linear, what we can do is that we can move this operator from here to here because the derivative is linear. So this would be equal to I convolved with the Laplacien of Gaussian. So this is how we got this name of Laplacien of Gaussian. Now the question is how to implement that for a discrete, for a two-dimensional digital image. Well, to answer this question, we have first to see the formula of the Gaussian. So it is given by a two-dimensional Gaussian is given by 1 divided by 2 pi square root of sigma, and this sigma is the variance, multiplied by the exponential of minus x squared plus y squared divided by 2 sigma squared. And Laplacien of this is just the second derivative in x and plus the second derivative in y. And if we do that, we would get this formula. So here we have x squared plus y squared minus 2 sigma squared divided by sigma to the power of 4 multiplied by the same term here. And this is basically the Laplacien of Gaussian formula. I'm missing a minus here. So that's it. Now, on a one-dimensional level, this Laplacien of Gaussian would look like this. So this is the Laplacien of Gaussian. And it can give us a good idea about how it looks on a two-dimensional level because it's isotropic. So here, the width of this is 2 square root of 2 sigma. Now this on a two-dimensional level looks like this. And it is called a Mexican hat filter. This is another name just because its shape is like a Mexican hat filter. Now the next step is to digitize this. The next step is to digitize this and get in a discrete form. So we would want to get something like this. And this thing can be written in the form of a mask or a kernel. So for example, a digital approximation of that function on a 5 by 5 mask would be this. So here in the middle I would have 16 surrounded by minus 2's, then minus 1's, and 0 everywhere else. Now, one thing that you need to check while approximating Mexican hat kernels functions in the form of a mask, a discrete mask, is to make sure that the sum of the elements in this mask is equal to 0. And this is an important property in any edge detector because it should give a 0 response in constant regions. So this is something to keep in mind. Now, let's discuss the effect of sigma. The effect of sigma first on the level of details. So when you increase sigma, what you are doing basically is that you are increasing the width of your Gaussian function, because sigma is given where the surface under the curve from 0 to sigma would be almost 35.2%. And the idea is increasing sigma would increase the width of the Gaussian kernel, and by doing so we are filtering out more high frequency components, right? And this is basically like filtering out more details, and this may be something bad to do because we do not want to filter out details of interest. So we need to fix the sigma wisely to remove as much as possible of noise while keeping the details that are of interest to us. Now, if you do that, if you increase the size of the Gaussian function, the Mexican hat filter would also increase in its width, because remember, the distance from here to here is given by 2 square root of 2 multiplied by sigma. And a wider Laplacien of Gaussian means that we would need a kernel of a higher size to approximate it, right? So, and the convolution requires n squared multiplications. So n squared multiplications are required for the convolution operation. So if we convolve, for example, the kernel that I've showed you earlier, the 5 by 5 kernel, with our image, we would need 5 squared multiplications, which is given by 25. So now let's say that I've gotten a wider Laplacien of Gaussian, so that I needed 15 by 15 kernel to approximate it. So in this case I would need 15 squared multiplications, which is equal to 225. And this increases, the number of multiplications required increases significantly with the size of the kernel, right? Not to mention that we have not only multiplications but also additions, because when we convolve we do multiplications and we also do additions. So in this context I'm talking about multiplications just for simplicity. Now, what we would do, instead of convolving the image directly with the Laplacien of Gaussian, what we would do is to use the separability property of the kernels. So instead of convolving the image directly with the Laplacien of Gaussian, we would convolve it with 4 one-dimensional kernels, and this would result in only 4 n multiplications. So for example, in this case, I would need only 15 divided by 4, which is equal to 60. So comparing this with this, we would have a gain of 4.25. So this would be 4.25 faster, and this is of course if we take just the multiplications, not to mention the additions. And as I said, that this gain gets bigger and bigger as we increase the size of our kernel. So now, so far I said that we use the Laplacian of Gaussian to get rid of noise. However, even if you use the Laplacian of Gaussian, even if you filter the noise, we would still get many false zero crossings, because we are not eliminating all the noise, we are just alleviating the effect of noise. And there are many sophisticated ways that tries to estimate the zero crossing that is as close as possible from the real one. And their problem is that they just give acceptable results. They do not give really good results. This is the reason why I'm going to ignore these methods and go and discuss with you in the next video probably the most used method to detect edges, which is called Canny edge detector. So this would be the topic of our next video.